Today we're going to start our notes on, this is really still Unit 1 as far as College Board is concerned, but we kind of broke it into parts. So we're going to talk about the rest of kinematics, starting with acceleration, because everything we've discussed so far has been moving at a constant velocity, and so we're going to introduce acceleration today. So that's what the warm-up question is regarding, is what is acceleration? How would you define that term based on what you already know or think you already know? Anybody want to share? Yeah, what do you got, Sophie?
It's a change in the rate of velocity.
Okay, change in the rate of velocity. Anybody else have something? Yes, sir. Velocity is increasing. Okay. Anybody else? All right, so we're going to talk about what that is today and about some very common misconceptions about, there are a lot of things that people think acceleration is, and we need to go over some of those things too to get rid of some of those misconceptions. So I would very strongly encourage you to jot this stuff down. Homework-wise, we do have problem set 202. Only part of it is available right now, and this is the portion that's in Mastering Physics. 202.3 is going to be posted later today. It is a graph match again, so I need to link the Desmos and I need to finish putting together the questions that go with it. And then 202.1 is the workbook practice that's on paper, and the copies weren't ready this morning, so we should have those tomorrow. But let's go ahead and get into our notes. So we've already talked about types of motion. And whenever we talk about an object that's in motion, there are different types of motion that we can discuss. The first being an object that's at rest. So in other words, it's not in motion. Its position is not changing. We also have talked about objects that are at constant velocity, and those are going to be objects where the position changes the same amount each second, meaning that you have a uniform change in position. And then the third type of motion is acceleration, which means that the position is going to change non-uniformly each second. So instead of saying that your position changes 2 meters each second, which would be constant velocity, we're going to have a non-uniform change in position, so it's not going to be that same increment each time. Okay, so this is what we're going to add to the discussion with our notes today is acceleration, because we've already talked about the other two, objects at rest and objects at constant velocity. All right, so here is a definition for acceleration that you may want to jot down. It is a vector quantity that describes the rate at which velocity changes, and that is the definition, or at least pretty close to what Sophie gave me a second ago. The equation for acceleration based on its definition is acceleration is change in velocity, or delta v, divided by t. It's the rate of change in velocity. And so it's change in velocity divided by time. You may also see this written as final velocity minus initial velocity, because that's what change in velocity is over time. And you do have this equation, but again, it's arranged differently, but it is on your AP Physics 1 formula chart. Misconception alert. Okay, first of all, acceleration doesn't always mean speeding up. Okay, that is a common misconception. And positive acceleration doesn't necessarily mean speeding up. Okay, nor does it mean that the object is moving forward. It can mean either or both of those things, but it doesn't necessarily mean, if you say that an object is undergoing positive acceleration, it simply means that the change in its velocity is positive, but that doesn't mean it's moving forward, because it could have a negative velocity with a positive change. Okay, and it doesn't mean that it's speeding up, because a negative velocity with a positive change would in fact be slowing down. So we're going to go over some examples, and I think it helps to put some data with it so you can kind of get a visual in your head. But again, it can mean either of those things. So again, acceleration is the rate of change in velocity each second. So here are examples of objects that would be undergoing acceleration. It would be objects that are speeding up, objects that are slowing down, and objects that are changing direction, because it is a vector quantity and the direction matters. If you have an object that turns, that object is accelerating, even if it turns while moving at a constant speed. Okay, so speeding up is going to happen when your acceleration is in the same direction as your motion. So if your motion is in the positive direction, you have a positive velocity, and you are speeding up, that means that you also have a positive acceleration. If, on the other hand, you have a positive velocity, you're moving forward, but your acceleration is negative, it's opposite the motion, then you would be slowing down. Okay, changes in direction, again, when an object turns, its motion in one direction will decrease as its motion in another increases, and again, velocity is a vector, so that is going to mean that you're going to have acceleration occurring when you have a change in direction. Again, when we put some numbers to it and some examples and some graphs, I think all of this, especially if you're a visual person, will be a little bit easier to understand. If you're not, it might make it harder, but we have to know how to do the graphs. All right, so here's what I mean. This is back to that common misconception. It is possible to have a large acceleration while moving slowly and vice versa. That is another common misconception, is that an object that has a large acceleration is moving fast. Not necessarily. Okay, and the second one being speeding up isn't always positive acceleration and slowing down isn't always negative. So there's a lot of misconceptions that are pretty common that relate to this unit. So if we look at this data table, and this is what I meant by looking at some numbers, you might want to sketch or draw this on your paper, but it shows an object moving for 4 seconds, and it shows its velocity changing from -20 to 0. And if you look at this, is this object speeding up or slowing down? So let's start there. If you go from moving at a velocity of 20 meters per second in the negative direction to 0, did you speed up or slow down? You slowed down. Okay, again, that negative sign is a direction. Okay, so -20 means you are moving 20 meters per second just in the negative direction. And yes, if you go to 0, you will not just have slowed down, you will have stopped entirely, but you slowed down on the way there. Okay, is this acceleration positive or negative? It is not negative, guys. Look at the numbers. What is my change in velocity each second? Positive what? +5. Okay, this is what I mean by misconception. Speeding up isn't always positive. Slowing down isn't always negative. Okay, this object has an acceleration of +5 meters per second, and it is slowing down, and those are both true simultaneously. It's also moving backwards. Okay, it's moving in the negative direction with positive acceleration. If those are opposite each other, you're going to slow down. So again, that's why I said you might want to draw this in your notes to have this table to look back at to remind you, because this is a very common misconception. All right. Remember, objects speed up when the acceleration is in the same direction as the object's motion. I just mentioned that. And they slow down when it is in the opposite direction. The positive and negative signs in physics show direction. In fact, -10 meters per second and 10 meters per second are the same speed. Okay, they're just opposite in direction. Okay, so again, take a look at this data table, different set of data from 12 to 9 to 6 to 3 to 0. Is this object speeding up or slowing down? Slowing down. Is the acceleration here positive or negative? Negative. This time it's negative because look at my change in velocity each second. It's changing by -3 meters per second every second. Okay, so this is my negative acceleration and slowing down. We just saw an example that was positive acceleration and slowing down. So it depends on both the direction of the motion and whether it is speeding up or slowing down. All right, so we can represent accelerated motion using the same tools we learned for constant motion. We have dot diagrams or motion maps. We have data tables, which we've already looked at a couple. We have position versus time graphs, velocity versus time graphs, and another graph that we're going to introduce in the notes today, and that is an acceleration versus time graph, which we didn't need to talk about in the last unit because all of our accelerations were 0, but now they're not going to be. Note, in this course, we only deal with uniformly accelerated motion. I am not going to ask you to do a calculation where the rate of change in velocity isn't a uniform value. Like all the tables I just showed you, each second the change was the same amount. If you were to do something with non-uniform acceleration, you would need calculus, and if you want to do that, you can take AP Physics C. Okay, but we're not doing it in here. All right, so again, just as a reminder, on a position time graph, your slope is velocity. We learned that in the last part, or in Unit 1, technically, the first part of this unit, although we're calling this 2. Okay, so acceleration again is the rate of change in velocity. So when acceleration occurs, that means the slope has to change. If slope is velocity and we're changing our velocity, our slope has to change. And when that happens on a position time graph, you get a curve. That is what this shows. Okay, so looking at this XT graph, and again, this might be a helpful thing for you to sketch out. We're going to sketch out quite a few graphs. Is this object speeding up or slowing down? It's speeding up, and the reason I know that is because if I look at my slope, it's getting steeper, and we know that a steeper slope means faster. We learned that in the last unit. So it starts out moving pretty slowly because it's a pretty shallow slope, and it gets steeper and steeper and steeper as this object continues in its motion. So that would have be an example of speeding up. All right, so here are, we're going to go over different possible scenarios. You can have an object that is speeding up while moving in a positive direction. And if you have that, obviously you have to have a positive slope on your XT graph. That's how you know you're moving in a positive direction, is that your slope is positive. But that slope has to change because now we're speeding up. So you don't have a constant slope, you have a curve. And if it's speeding up, it needs to get steeper. It's going to look like the graph we just looked at. Okay, reminder, speeding up tells us that acceleration and velocity must be in the same direction, which means that I have positive velocity and positive acceleration here. I know I have positive velocity because it says I'm going in a positive direction. I know I have positive acceleration because it says I'm speeding up while going in that positive direction, and that means that the signs have to be the same. Okay, so again, this is the first example scenario that you'll encounter is an object that is speeding up while moving in a positive direction. That object would have both positive velocity and positive acceleration, and its XT graph would look something like this, although it doesn't have to start at 0. Again, that's just the initial position. It could be down here. That's still going to be an example of an object that is speeding up in a positive direction because it still has a positive slope overall. I know it's changing slope, but the slope is positive the whole time. And that slope is getting steeper the whole time. So again, it doesn't have to start at the origin. That just indicates that it started at the reference point, but it doesn't have to. All right, so here is what our XT graph might look like. What would the VT graph look like? Okay, well, as a reminder, positive direction on a VT graph means we are on the positive region of the graph. We have to plot our points up there. Okay, and if I want the object to speed up, that means that I want the object to move away from 0, because guys, how fast am I going if I'm going 0? I'm not, right? Okay, and so if I want to speed up, it needs to move away from 0. Okay, so this would be an example of an object speeding up from rest, and I know that because I had it start at the origin, but that is an object that is speeding up in the positive direction. Okay, it's moving forward the whole time because the line is above the x-axis the whole time, and it's moving away from 0, so it's getting faster. So maybe my velocity started at 0, and then it was 1, and then 2, and then 3, and then 4, or whatever. Again, this would also be speeding up in the positive direction. I don't have to start at 0. Okay, the graph could be plotted anywhere, depending on the scenario. All right, so again, this means that I have positive velocity and positive acceleration. Again, I know my velocity is positive because I'm in the positive direction. I know my acceleration is positive because I'm speeding up. That means they have to have the same sign. All right, so looking at a VT graph again, okay, we've already talked, well, we haven't talked about this last bit. But remember, a VT graph plots velocity on the y-axis and time on the x-axis. The x-axis represents 0 velocity when the object is at rest. Okay, so what is the meaning of the slope on a VT graph? We haven't talked about that specifically yet because last unit, all of our slopes on our VT graphs were 0. And that's because last unit, all of our objects were moving at a constant velocity. But if you look at these, the axis here, if you were to find the slope, that would be the change in y over x. That would be change in velocity over time. What is that the equation for? Acceleration. Okay, so the slope on a VT graph will give you acceleration. And again, this is just a reminder of VT graphs. We just looked at one. But all of your positive velocities will be up here. That means forward motion. All of your negative velocities will be down here. That means backward motion. And anything on that line for 0 is, of course, at rest, either temporarily if it's just crossing it for a moment, or maybe it's sitting there for a bit. Depends on the graph. Okay, reminder, you cannot determine starting position from a VT graph. Okay, I don't know where these objects start. I only know how fast they are at time of 0. I would not know their initial position unless I had an XT graph to accompany it, or if that information was provided to me in the question. All right, so again, the slope gives acceleration. It is rise over run, which is the equation for acceleration, change in velocity over change in time. Questions about that? Okay. All right, note we only deal with constant acceleration. I already mentioned that, so all of our VT graphs will have straight lines, okay? We will not see a curve on a VT graph. You will see curves on an XT graph, but not on a VT graph. So this would be an example of an object. Actually, I'm going to ask you, is this object speeding up or slowing down?
Slowing down.
Slowing down, because it's actually stopping, okay? It's moving forward, and it is slowing down. And it has a uniform change in velocity, which means it has constant acceleration. All right, so let's look at slowing down in the positive direction. That's what we just looked at. It looks like this, slowing down in the positive direction. I know it's positive direction because it's up here. I know it's slowing down because it approaches 0. What does that look like on an XT graph? Well, again, I don't know where to start this graph because it doesn't tell me, so I can start it anywhere. Okay, and by the way, again, this could also look like this. It doesn't have to be where I drew it. It doesn't have to go all the way to stop. Okay, it just needs to have a negative slope to it to show that it is negative acceleration, or that it is approaching 0 in this case. All right, so if I want to show slowing down in a positive direction, again, positive direction means I'm going forward. So that means on my XT graph, I need a positive slope. Okay, and in order for it to slow down, that slope has to get flatter. It has to get less steep. So something like this would be an example of an object that is slowing down in the positive direction. I know it's moving forward because my slope the entire time is positive, even though it's changing in its steepness. It's positive the whole time, so it's forward the whole time. And it gets less steep, and therefore it slows down. Again, I could start this graph anywhere. This would also be an example of an object that is moving forward and slowing down. Okay, in this case, in both of these, my velocities are positive. Again, I'm going in the positive direction. I'm going forward. But my acceleration is negative. Again, these will have an opposite sign if you're slowing down. All right, next example would be slowing down in a negative direction. We're just going to go through all the possible combinations here. Okay, if I want to slow down in a negative direction, first of all, negative direction tells me that I have a negative velocity and thus a negative slope on my XT graph. If I want to slow down, that slope needs to get flatter. This would be an example of what that might look like on a position time graph. And again, it could be drawn anywhere on that graph, so that's fine too. That object is also slowing down in the negative direction. On my VT graph, I need to draw my graph in the negative region of the graph to show that I'm moving in the negative direction. And in order for me to show an object that is slowing down, it needs to approach 0. Because 0 means I stopped. And so this is what slowing down in the negative direction looks like. You'll notice it has a positive slope, which means it has positive acceleration, which again makes sense because I have negative velocity. If I'm slowing down, my acceleration needs to have the opposite sign. Again, sketch out whatever amount of this you want. I know there's a lot in here, so I'm going to go through it kind of fast. This is slide 147, by the way, and it's from the slide y'all already have. We didn't separate it out yet, because last year we did it all as one unit. All right, so what about speeding up in the negative direction? Again, negative direction means negative velocity, and on an XT graph, that means a negative slope. And that slope needs to get steeper because steeper means faster. Something like this would be an example of an object speeding up in a negative direction, or that. Those are both examples. If I wanted to draw this on a VT graph, again, negative direction tells me I'm in the negative region of my graph, that I'm moving backwards. And I'm speeding up, so I need that velocity to move away from 0. Maybe I started at -2 and it's now -3, -4, -5. I'm getting faster, but I'm moving backwards. Okay, so this would be an example. Again, it could start at 0. That's fine too. Depends on what scenario you're looking at, but these are both examples of something speeding up in the negative direction. Again, my negative direction tells me negative velocity. Speeding up tells me that my signs are the same. So this is an example of both negative velocity and negative acceleration. And I can see that acceleration in the slope of my VT graph because I have a negative slope. All right, what if we change direction from a positive velocity to a negative one? What if I throw a ball up in the air? It goes up and then it comes back down. Okay, what does that look like? Well, my slope would have to change from a positive slope to a negative one. That ball would have to stop momentarily before it turns around, so that positive slope would have to get flatter and flatter until it was completely horizontal, at least for a split second, and then it would start to get steeper in the other direction. It would look something like this on its way up and like that on its way down. Okay, and it doesn't have to be a ball. Anything that is going from positive velocity to negative velocity, it would look something like this. The entire time, this would be an example of negative acceleration, because as I have this object slowing down with positive velocity, slowing down means opposite sign, that's negative acceleration. This one is speeding up with negative velocity. Speeding up means same sign, negative acceleration. Okay, so those would both be negative acceleration. On a VT graph, I would have to start in the positive region of the graph and go cross the x-axis into the negative region of the graph. That means this object started with a positive velocity, slowed down until it stopped for a moment, and then started speeding up in the negative direction. Okay, again, if you change direction, you have to cross the x-axis. Again, the slope of a VT graph is acceleration, so this is an example of negative acceleration. It's negative the whole time. And for a ball thrown up in the air, that acceleration would be caused by the force of gravity, which we will talk about later. All right, what if you go from a negative velocity to a positive one? Okay, maybe I throw a ball down at the ground and it bounces back up. Okay, if I call down negative. So again, it would look just the opposite. It would start out with a negative slope that flattens out, and then it would have a positive slope that gets steeper. This is positive acceleration the entire time, and this is an object changing direction from a negative velocity to a positive one, and this is what it looks like on an XT graph. The VT graph also looks the opposite of the one we just looked at. My VT graph would look something like this. Again, because it's turning around, you do have to cross that x-axis, but this time it started in the negative region and went into the positive region because it went from negative to positive. Again, my slope is my acceleration. This has a positive slope, and thus this is an example of positive acceleration. Okay, so let's see if we can analyze an XT graph like this one. Okay, I've got some questions up here. What is the instantaneous velocity of the object at 6 seconds? Well, you can tell that this velocity is changing quite a bit because my slope is changing. This is like a really weird looking curve. And so if I ask you for instantaneous velocity, I want to know what the velocity is at that instant, specifically at 6 seconds. And so you would look at 6 seconds. This is a position time graph. And so if I want to figure out velocity from a position time graph, I would need slope. Okay, and so this is, luckily for me, a fairly straight line segment. So I could pick 2 points on this line segment, and I could calculate my slope there, and that slope of that segment would give me the instantaneous velocity at that moment. Okay, so that's how you would answer that question. It looks, again, something like that. You'd have to find the slope of that segment. And you could extend it out on your paper with dashed lines to find grid lines that it crosses through. I don't think I have the answer on here. Okay, when is this object accelerating? Anytime this graph curves. If you see a curve, there's acceleration happening. Okay, when does the object have constant velocity? Anytime that this graph has a straight line segment. There aren't very many of them in there. I highlighted one a second ago. Okay, and then when does the object have an instantaneous velocity of 0 meters per second? What do you guys think about that one?
At the top or bottom of the curve?
Yeah, any of those curves that like changes direction, the top or the bottom, because if you look at the slope at that point, you would have to look at the tangent line. Y'all know how to do that, right? To sketch a tangent line where it only crosses through that portion at one point. But that would be your tangent line for that point that I just picked. And so my slope at that point would be 0. And just think of it's turning around. It has to be 0 at the top of that thing, or at the bottom of that one, for example. Same idea. Okay, so the instantaneous velocity of 0 would be at those points. I don't know if there's another one on here, but at those there are. All right, which of the following are examples of positive acceleration? Okay, I've got some options here. I want you guys to think about this one. Object moving upward and slowing down, an object moving backward and slowing down, an object moving forward at a constant velocity of 5 meters per second, or an object moving east and speeding up. We're going to assume for the sake of this question that forward is positive, backward is negative, upward and east are both positive. Okay, so which one of these would be positive acceleration? What do y'all think? Could be more than one. Well, let's start, we'll go one at a time since we're quiet today. Up and slowing down, is that going to be positive acceleration? No, because that's going to be something that has a positive velocity, but if it's slowing down, that means the acceleration has the opposite sign, which means it'd be negative. Okay, what about an object moving backward and slowing down? Is that positive? Well, let's see, backward might mean -5, and slowing down would be -5, -4, -3, -2. Is that positive? Yes, that change in velocity is positive. Okay, and then forward at constant velocity, obviously no. East and speeding up, that's the easy one. Yeah, that one's definitely positive acceleration, but so is this one. Okay, backward and slowing down is also positive acceleration. Again, this is that example from earlier, or a similar one if you need to copy it down. This object is moving backward and slowing down. It has positive acceleration. Specifically, its acceleration is positive 2 meters per second every second. Negative velocities mean an object is moving backwards. Slowing down means velocity is getting closer to 0. I already answered the last question. The acceleration of this object, positive 2 meters per second per second. Questions about that? I told y'all it was going to be a common misconception. Some of y'all already forgot, even though we already talked about it. That's okay. It's the first day. But you definitely don't want to get tripped up with that because you will miss questions on a test. All right, here's a VT graph with a couple practice questions. How far does Polly travel after 5 seconds? Again, as a reminder, on a velocity time graph, if you want to find displacement, you would have to find the area of the rectangle formed here, the area under the line for Polly. So Polly, if she travels 1 meter per second for 5 seconds, will go 5 meters. That one's pretty easy. But you're finding the area anytime you multiply those axes, and velocity times time is going to give you displacement. That's the equation for it. Okay, so displacement is velocity times time. That is my y-axis times my x-axis. So if I find that area, I will be finding displacement, and that's length times width. 1 times 5, which of course is 5. Art is accelerating. Okay, you can do the same thing though. You still find the area, but for art it's a triangle. 1/2 base times height. Okay, his average velocity for this entire trip, if he goes from 0 to 2.5, his average is 1.25. That's half his final velocity times his time. That's the equation for a triangle, 1/2 base times height. So that 1.25 times 5 gives me his, and again, this is this equation. 1/2 base times height gives me his displacement. All right, here is another velocity time graph. I don't know if we have enough time to go through all these questions because I'm trying to make sure we get to the end of the notes. But it says, what is the acceleration at 10 seconds, which would be at this point right here? Guys, if you want to find acceleration at a specific point, and it's on a line segment, you just have to find the slope of that line segment. Okay, it doesn't have to be the slope at that point if it's not on a grid line, although this one is. Okay, but pick any 2 points on this segment, and all of the points that fall on that segment share the same acceleration because they all share the same slope. Okay, so you could get that, let's see, it goes from 20 down to 0, and it does so over 4 seconds. Negative 20 divided by 4 is negative 5, so its acceleration would be negative 5 meters per second every second. Okay, find the displacement from 4 to 16 seconds. Again, this is a velocity time graph, so the displacement is the area. From 4 to 16 is going to be a trapezoid shape over here, and then this flat part, but it's really just this part here. And so you would want to find that area. Why did I mark that? That's not 16. All right, there. I think I need to move that line over, but the area of that right there. And I would do the area of that rectangle, the area of that triangle, and add them together, and that would give you your displacement. We don't have to do anything for this part because when the velocity is 0, we're of course not changing our position, so we don't have to worry about that, but we do have to add these. When does this object slow down? What do y'all think? When it gets closer to 0. From 8 to 12, this is slowing down. But so is this, from 22 to 30. Okay, so again, slowing down doesn't mean negative slope. It just means getting closer to 0. Okay, acceleration would be negative, though, if there was a negative slope. Okay, so acceleration is negative when my slope is negative, which would be here from 8 to 12 and here from 16 to 18. But that does not necessarily mean it's slowing down. All right, those are my negative accelerations. And again, the parts where it's slowing down are the parts where it approaches 0. So going back over it, you got to be able to apply it. Okay, as I said, we have a lot to go through. The last type of graph we will use to show motion is an acceleration time graph, or an AT graph. This graph plots acceleration on the y-axis and time on the x-axis, and this course only deals with constant acceleration, so all of our lines will be horizontal. That makes it easy. Okay, because we have constant acceleration in all of our examples, you will never see a sloped line on an acceleration time graph, at least not one you'd have to calculate. If you got one, it would be a concept question. Is this constant acceleration? No. Okay, but you won't have to do any calculations. They can be in the positive region, negative region, or on the x-axis. You can still interpret slope, but since all lines are horizontal, all of our slopes will be 0. All right, so again, the x-axis represents 0 acceleration. We're going to sketch out some AT graphs. 0 acceleration, what does that mean? Okay, it means the object has constant velocity or it's at rest. That's what it means. Okay, so if you have an AT graph with your data on the x-axis, that object is either moving at a constant speed or it's not moving at all, but you don't know which if all you see is that. Okay, you can't tell which one it is. You just know it's one of those two. It's not changing its velocity. That's all you can see. You don't get much information from an AT graph. Okay, again, anything up here is going to represent positive acceleration. Anything down here is going to represent negative acceleration. Note, you can determine neither starting position nor displacement from an AT graph. So we have even less information than we did before. We lose a little bit each time. Okay, our XT graph shows us a lot. VT, we can't see starting position. AT, we can see even less. We don't know starting position. We don't know displacement. We don't even necessarily know which way the object is moving. We only know what the direction of its change in velocity is. All right, so here is what an AT graph looks like for constant forward motion. You already have some other graphs. You can add this one to it. Constant forward motion means I'm not accelerating, so I would have 0 acceleration. My slope will be 0 and my line will be on the x-axis. Something at rest will look exactly the same. Okay, so again, this is for anything that is not accelerating. Moving backward with constant velocity will look exactly the same. Okay, there's no difference in the AT graph. It doesn't give us very much information. Okay, so this is what it will look like for anything with constant forward velocity, constant backward velocity, or something that is at rest. All right, looking at this AT graph, do we know if this object is speeding up or slowing down? What do y'all think? We do not. Okay, I have no idea because I don't know which way it's going. Okay, I don't know what its velocity is. All I know is it has a positive acceleration, and we learned earlier that positive acceleration doesn't necessarily mean speeding up or slowing down. It could mean either. Do we know which way it's going? No, we do not. Okay, again, we don't get much information from this graph. Positive acceleration means the object's velocity is getting more positive. That's what we know. Okay, that could mean that it's slowing down because it was moving in a negative direction. But that could also mean that it's speeding up because it was moving in a positive direction. We've already talked about two examples of this. Speeding up in a positive direction, of course, would have this AT graph. You'll notice that the slope of this VT graph is a positive slope. If this slope happened to be positive 3, well, guess what? This is at 3. Okay, that would be at A equals 3. But speeding up in a positive direction, this is what your VT and AT graphs would look like. Please note, and I mentioned this already, the slope of your VT graph gives you acceleration because of this equation. The slope of this line is rise over run, change in V over T. However, you can also get information from this. Not a lot, but the area under the line on an AT graph will give you your change in velocity. Just rearrange the equation. Anytime you multiply your axes, you find area. Anytime. Okay, so A times T is the equation for delta V if I rearrange this equation. Therefore, that area has meaning. It tells me my change in velocity. It doesn't tell me how fast I was going initially, but it does allow me to figure out what the change in velocity would be. Okay, so you can use the slope of a VT to find acceleration. You can use the area under an acceleration graph to find your change in velocity. All right, here is the graph for slowing down in a negative direction. Notice I did not change my AT graph at all because it's exactly the same as it was for the other example, because look, this still has a positive slope. Okay, slowing down in a negative direction has this VT graph and it has this AT graph. Slowing down in a negative direction, again, slowing down means acceleration and velocity are in opposite directions. They're offsetting each other. Negative direction means negative velocity, so your acceleration must be positive. In order for it to slow down, your signs have to be opposite. We're going to come back to that over and over again. Use it. It's a trick. It'll help you, okay, whenever you're answering questions. All right, again, back to our misconception. Slowing down in the negative direction is positive acceleration. Here's that same data. Negative 12, negative 10, negative 8, negative 6, negative 4. My change in velocity each second is positive 2 meters per second each second. That's my acceleration. On an AT graph, it would look like this with a y-intercept of 2. Okay, so again, back to that misconception. When might you have this? If you have an AT graph with a negative acceleration, it could be an example of an object moving forward and slowing down. Again, forward means positive acceleration, positive velocity. Slowing down means that my acceleration has to have the opposite sign. It could also be an object moving backward and speeding up. Okay, both of those would produce this exact same graph. Okay, so look back at the slopes of the VT graphs. You'll see it. Both of the slopes of these two graphs I described on my VT graph had a negative slope. All right. Here is what that activity that I said would be posted later today is going to look like. You're going to have an XT graph, and you're going to be asked to match it up with a VT and an AT graph. So you do need to be comfortable with all these graphs. That's why we spent so much time on them today. You might actually want to add this to your notes. Given the XT graph below, draw the VT and AT graphs that show the same motion. Then describe in words the motion of this object. I'm going to give you all a moment to try this. Okay, we just went over a bunch of notes kind of fast. Okay, so I want you to try it out, see how you do with it, see if you can figure out how to draw the VT graph first. I would definitely do that first, and then from there, what the AT graph would look like that also shows that same motion. I'm going to give you all, 45 seconds to see if you can sketch something out, and then we'll go over it. Okay, let's start with the description of this object's motion because that might help us with our graphs. This object starts out at the origin, which isn't as useful because that doesn't show up on my other graphs, but it starts out at the origin or at the reference point, moving very slowly in the forward direction because the slope is almost 0. Okay, but it's a little bit of a slope. So it's moving forward very slowly, and then it starts to curve here, and it gets steeper, which means it speeds up, moving forward. And then this part's kind of straight, so it maintains a constant forward velocity. And then, look at my slope, it flattens out. It slows down, almost to a stop. Okay? So if I wanted to put this on my VT graph, first of all, everything on this graph is forward. So everything on my VT graph has to be above the x-axis, all of it, okay? Because there's no point at which this graph goes with a negative slope, okay? Again, the slopes here tell you your velocities, which means my starting velocity is almost 0, okay? For this section, it's almost 0 and it starts to speed up. I'll say it's 0, close enough, and it speeds up, okay, moving forward. And then right here in this next section, it maintains a constant forward velocity. Well, on my VT graph, that's going to be a horizontal line, constant forward velocity. And then it slows down, still moving forward, but it's going to slow down, we'll say to a stop, which means it goes back to 0. Okay, again, you need to be able to do that. Okay, go through that thought process so you can sketch it out as well. Okay, so again, this object is moving forward the whole time. It speeds up, it moves at a constant velocity, and then it slows down forward the whole time. Acceleration, if you have the VT graph, acceleration's easy. Use the slopes. Positive, 0, negative. That's my acceleration graph. The first line segment here is a positive slope, so my acceleration initially is positive. My acceleration for this portion up here is 0 because it maintains a constant velocity. It's not changing its velocity there. My acceleration for this portion is negative. Look at the slope. Okay, it would look something like that. Are there questions?
Do you draw the lines to connect?
You can. She asked if you draw lines to connect these. You can. This is not possible. Technically, this graph would have a curve if it was actual data because it's not possible to just go in the same way you can't, start moving without accelerating first. In last unit, we kind of simplified that. It's the same idea here. That acceleration isn't actually uniform, but for our graphs it is. If you want to connect them with a vertical line, you can. You do not have to. This is acceptable. If you connect it, it is also acceptable. Just make sure that in the real world, that line would have a slope to it. It wouldn't be vertical. You can't simultaneously have an acceleration of 5 and 0. Okay, but for us, we're not dealing with changes in acceleration, so this is what our graphs are going to look like. It's an oversimplification for now, for this course. If you take more physics, you see something else. All right, so this object's moving forward, speeding up before traveling at a constant velocity forward, then it continues forward and slows to a stop. Okay, that's what we said was happening. All right, that is it for the notes today. I told you it was going to take most of the period. We have 7 minutes left. You are welcome to open up the Mastering Physics assignment if you want to take a look at it, because you do have that, or maybe you want to take a look at your lab before you leave. But you have, like I said, 7 minutes left, so if you guys have any questions, please let me know.